So section 2 is probably going to be where we spend most of our time here, trying to become familiar with how to name, how to draw various types of hydrocarbons. Specifically, we're going to learn about alkanes, alkenes, alkynes, and talk about some of the properties of each of those. So hydrocarbons, to define them, they are compounds that only contain carbon and hydrogen. They're the simplest class of organic compounds. So again, we're just giving kind of a base level of what OChem would be like. They get more complicated though. And you can start to see, you can make any combinations of these things. That's why there's so many different organic compounds out there. First one, saturated hydrocarbons. This is where each carbon atom in the molecule forms 4 single covalent bonds with other atoms. So the carbon would be completely saturated, meaning all 4 of its connection points, as I call them, would be with either another carbon or with another atom. So there's a couple examples of saturated hydrocarbons. Notice there's only single bonds involved. So this carbon is attached to 3 hydrogens and a carbon, making it saturated. Also, each of these carbons in the propane do the same as well. Notice that they only differ, ethane and propane only differ by 1 CH2 between them. I've basically just taken ethane, added a CH2 in the middle, and now it's propane. So things that differ by like this are homologous series. I could add another CH2 somewhere in here and add another one and another one. And you're going to see I keep kind of leveling up, having 1 more carbon each time, but 2 more hydrogens each time. So there is a little bit of formula if you see that pattern. We see that the straight chain alkanes are going to have C with a number, and then we just double that number and add 2. That tells us how many hydrogens we have. So ethane, we saw, it had 2 carbons. We double it and add 2, we get 6 hydrogens. Propane has 3 carbons. We double it and add 2 to give us 8 hydrogens. As you can imagine, I'd take it one further, which would be called butane. We have 4 C's, C4. What do you think the H would be? It'd be doubled, add 2. So you'd have, and we saw this earlier, C4H10 for butane. And there they are there for you. The homologous series of methane, ethane, propane, and butane. You have to definitely remember those 4, and then we go further into pentane, hexane, heptane, octane, all the way up to nonane and decane for 10. One type of alkane we want to talk about also is a cycloalkane, which means the carbons are arranged in a ring. They are often drawn in a simplified form, these skeletal representations I've been talking about, where we have this thing called cyclopentane. The 5 carbons, as you see, are arranged in a pentagon, but I can assume that each one has its 2 carbons, and each one will also, 2 single bonds to other carbons. The other 2 will be hydrogens for each one. This is called cyclopentane, and I can simplify it by literally just drawing a pentagon, because that's going to show each bend in my pentagon is going to have a carbon, and then each one is going to be linked to 2 hydrogens. So cycloalkanes is not quite like the regular, the butane, for instance. Butane has a straight chain of C4H10. Cyclobutane has a circular pattern with 4 carbons to make it cyclobutane, but notice we don't need as many hydrogens to complete all the chains. So it's going to have 2 less hydrogens. So butane is C4H10, cyclobutane is only C4H8. So systematically, how we're going to name them, according to IUPAC, the IUPAC, the International Union of Pure and Applied Chemistry, it's going to allow us to avoid some of the ambiguity that could come with naming these structures. So the first one we'll look at here, an example, heptane. Heptane has 7 carbons. Again, the ending carbons have 3 hydrogens around them, and then each of the middle carbons are attached to 2 hydrogens. So heptane's formula would be C7H16. What we do is we just take that prefix and add ane to the end, so heptane. So we already talked about methane, ethane, propane, butane, pentane. Notice how that melting point, it goes down the more carbons I add, because it allows for more hydrogen bonding. The boiling point does increase as I go down because of that. And we see that it continues to increase and increase as I go from hexane to heptane to octane to nonane to decane. So you might want to have these charts memorized to a degree, or at least written somewhere when you're doing your homework, to be able to name them. We have another handy chart which we'll talk about in a second. It has at least the first 5 of these. And we're going to talk about these branches now. These are called alkyl groups, which are basically branches off of the alkanes. And they're similar in a way. They're just missing a hydrogen, because instead of being by themselves, they're branches. So they're branching off of a carbon. So methyl is like methane with one less hydrogen. Methyl is going to be branching off one of these. It's a group that branches off the main structure. Ethyl, just like ethane, propyl, is like propane, butyl with the prefix of butane, pentyl with pentane. They're going to branch off. These 5 down here can branch off some of these 5. So what we're going to do in order to name a molecule is there's a couple steps involved. We're first going to locate what's called the parent hydrocarbon, and that's the longest continuous chain that has the most straight chain branches. So for this one, it's very tempting to go ahead and just say, well, this is the longest straight chain, right? I have 1, 2, 3, 4, 5, 6, 7, 8. So I think I have octane. However, the problem comes when I see this down here. This forms a T. The one that's branching off of this carbon is forming a T down here. I don't want that. So the better way to branch this would be to go 1, 2, 3, 4, 5, 6, 7, 8. Notice I still have octane, but now if I go that way, I only have straight branches off the ends. I don't want to have any T's involved. I only want straight branches. So what I put in like that rectangle shape there, that's going to be my parent hydrocarbon, and I'm going to call that octane. I think the notes show you want that branch, not that branch. Hopefully you see the difference. We want the one that only has straight chains coming off of it, not the one with a T coming off of it. So here are my... So first, I know it's octane. The next step would be to find my alkyl groups. And this is where that chart might come in handy on slide 26. A lot of people refer to this slide 26 because you're going to start to recognize these, but you have a methyl group, an ethyl group, a propyl group, a butyl group, and a pentyl group. And it can go further, just like the alkanes do. But I see here that I have a CH3. That's a methyl. It's a methyl. So I have 3 methyls, and I have a CH2CH3, which is an ethyl. So there's an ethyl group, a methyl group, and then two more methyl groups. You see that down there. Three groups are methyl group, that's CH2CH3 is an ethyl. Methyl and ethyl. So how we're going to name this, we're going to put them in alphabetical order. So the groups, ethyl always comes first, then methyl, even though methyl is only one, because we have to put them in alphabetical order. If there was a butyl group, then butyl would come first. If there was a propyl group, then propyl would come last. It's just the way they decide to name them. So then once we put them in order, we're going to count how many we have and put a prefix in front of it. Since I have 3 methyls, I'm going to call it trimethyl. I don't have to put anything in front of ethyl. So right now I have ethyl trimethyl octane. We're still not done yet. There's one more step. We have to say where the chains are. So there's 2 options I have when numbering the chains. I can either go from one side all the way to the other. So you see they started here and they went left to right essentially. Or you could start from right to left. Why did I pick right to left and not left to right? Well, you got to think, you got to remember these molecules, they're drawn on paper a certain way, but in 3D space, we don't know what way it's turned, which way it goes. So I can't just say, well, name it from left to right or name it from up and down. We have to have a common way of numbering these that makes sense to everybody no matter how they're looking at the molecule. So the reason I chose the way on the left is because it gives the branches lower numbers. That's always the rule of thumb. Sometimes there's some gray area there, but what you're trying to do, since you know there's a branch here, and a branch here, we have a branch at 2, 4, and 5. This way of numbering gives me a branch at 4, 5, and 7 carbons. And I'm numbering the carbons, by the way. I don't like having high number branches. I like having low number branches. So how we're going to name this then is going to be, it's going to be 2, 4, 5. Or actually, let me back up there. I forgot. There's also a 3. I forgot these are my 3 methyls, and then there's an ethyl coming off of the 3. So let's name the ethyl first. Sorry about that. The ethyl, it's going to be 3 ethyl, and then put a dash there, 2, 4, 5 trimethyl, and octane. Trimethyl octane is one word, but it's 3 ethyl, 2, 4, 5 trimethyl octane. Go ahead and pause that here if you're not making sense of it. See if you can see where I got everything. Let me know if you have any questions. Here's the answer there. 3 ethyl. It's better than my scratch writing there. But it's 3 ethyl, 2, 4, 5 trimethyl octane. Separate your alkyl groups with hyphens. Separate your numbers with commas. And there's the picture of it so you can take a look. So let's try to name this one. This one is a little easy. I have my single chain. I see this one looks pretty good. I don't see any issues with that. They're all straight chains off of it. Notice I could also choose this one coming down, and it would still be the same. Same thing, either way. So this is 1, 2, 3, 4, 5, 6. I have 6 carbons there. What I call that parent chain is a hexane. So my name is going to end with hexane. I notice I have, how do I number it? So I could go left to right, and that would mean I have a 2, a 4, and a 5. Or I could go right to left, and I have a 2, a 3, and a 5. I'm going to go right to left because it's slightly better numbers. So 1, 2, 3, 4, 5, 6 is how I'll number my carbons. I should be drawing that in a better color. But I see these are all methyl groups, all just plain old CH3s. So again, it's going to be trimethylhexane. And 2,3,5 is going to be my number. So it's 2,3,5 trimethylhexane. That's how you would name that one. We're going to have a whole slew of practice problems to go over these. I have a little worksheet packet for you that's got kind of a how to do, and then the rest is doing it on your own. But again, please feel free to ask me if you have any questions. We're going to talk about alkenes and alkynes in a second, but just to go over, some of the uses of alkanes. They are typically nonpolar because the only forces of attraction between nonpolar are those London dispersion forces. These forces are stronger when those molecules are larger. That's why you saw those higher boiling points, because these tend to be in liquid form at that point. The lowest mass, though, it typically gases. You think of like your butane, for instance, is a liquid, but methane would be a gas. Things like gasoline and kerosene, they're much more kind of mixtures of some of those. Natural gas is primarily composed of alkenes with 1 to 4 carbon atoms. Then the larger ones like gasoline and kerosene are typically liquids. You can even have such large ones like huge numbers of carbons, like in the 50s, that are solid because they're paraffin wax, for instance. Yeah, so the hydrocarbon molecules in petroleum contain from 1 to more than 50 carbon atoms. A lot of times you see, those numbers, the octane number has to do with the mixture of what you're seeing at the gas station, whether it's 89, 93. Kind of gives you an idea of how much octane is in your gasoline mixture. But there's this idea of fractional distillation, which is separating those components of the mixture by, they're separating by boiling point, basically. So now we're going to get into unsaturated hydrocarbons. This is where we don't have the maximum amount of hydrogens, and we start to form double bonds, triple bonds in between the carbon atoms. So an alkene, well, first of all, the one on the left is alkane we're familiar with. It's propane. Let's make this into an alkene. Let's get rid of 2 hydrogens, and instead of C3H8, we're going to have C3H6. So now we have that double bond there that has replaced 2 hydrogens. So my formula now, all I'm doing for an alkene is I'm doubling the carbon instead of doubling it and adding 2. So what's important to name the alkene is where does that double bond take place. So for instance, for pentene, I see that if I name this, I could go left to right, or I could go right to left. I'm going to go left to right. Notice we have to name it by the double bond, first of all. I don't want to name it by any single bonds because I don't have a name for this double bonded branch. I have to look at where the double bond is, make the double bond part of my parent chain, and then put a branch off of that pentene rather than calling it hexane. So always put the double bond in your parent branch. But then as far as numbering goes, I want the double bond to have the lowest number. So here I'm going to call it 1 pentene rather than 5 pentene. And because now we named it left to right, I see I have an ethyl group, so we're going to call it 2 ethyl, 1 pentene. If I have 2 double bonds, I'm going to name them both. I'm going to include both. So again, use the lowest number of the double bond. I see a 1 and I see a 4. Don't use the 5, use the 4. And that's going to be 1,4 pentadiene, because the di tells me I have 2 double bonds. So you see diene for 2 bonds, triene for 3 bonds, and so on. So it gets a little tricky, like you have tetrene or something. It gets a little tricky with the multiple double bonds. But that's how we name them, to be systematic. So let's take a look at this one. You can see my parent chain has to include the double bond. So I'm going to include these 4. Remember, 4 means butane, but this is an alkene because it has a double bond. So we're going to call it butene. And I see I have a chain off of here. I have a chain off of here. This is a methyl. This is an ethyl. So first, let's name the butene where its double bond is. I'm going to go this way, 1, 2, 3, 4, because I want that double bond to have the lowest carbon number. So it's going to be 1 butene, and with my branches, we only have 1 methyl and 1 ethyl, so let's call it 2 ethyl, 3 methyl, 1 butene. So it's 2 ethyl, 3 methyl, 1 butene. So what are the properties of alkenes? They, again, are nonpolar, and they're similar to alkanes in terms of their boiling points and physical states. An example, it's not pictured there, but alpha farnesene, which I believe means 15 carbons, is a solid at room temperature. We find that as like a natural wax covering on apples. So last one here, we have alkynes. These are now with triple bonds, and they're going to have very similar properties to alkenes on how we name them, for instance. It's just now we actually have less hydrogens than we do carbons, so or at least in most cases. In the case of acetylene, we have C2H2. You notice you have a triple bond between the 2 carbons and the 2 H's on the outside edge. Some more examples of alkynes, you have 1 pentyne, which has, notice, it's 5. It's a 5 carbon chain, and that triple bond happens on the first carbon, the lowest carbon. This one, it happens on the lowest carbon, so we're going to call it 1 butyne because there's 4 carbons. There is a methyl group off the 3rd carbon, so let's call it 3 methyl 1 butyne. And then there's this last idea we want to talk about. It's called an aromatic hydrocarbon. You know, it's a chain where you have this double bond between the 2 carbons. It can happen either here, here, and here, or it can happen here, here, and here. So this is called benzene. It's C6H6. And it's actually a resonance structure because of those double bonds can occur in multiple locations. And here's kind of a simplified structure of that. But that's really all we're going to do with those 2 sections. And then next, we're going to move on to functional groups. So really kind of one of the last topics we'll be talking about this year.